And that talk will be in this location with lunch served at the same time. But right now, it's my pleasure to introduce Jeff Vaughan, who is a new Circus Fellow just starting this semester. Jeff is with an Epsilon of finishing his PhD from the University of Pennsylvania. And his work is really at the intersection of programming languages, security, and formal methods. And today he's going to be talking to us about a project right there in that intersection, a system called Aura that he's been working on for the last few years, which is using programming language techniques to specify and enforce very rich security policies for purposes of authorization, access control, and audit. Without further ado, thanks very much, Steve.
Thanks for the introduction, Steve. So, as Steve said, I'm Jeff Vaughan, and I'm going to be talking about the system called Aura, which is actually my PhD research. And Aura is all about trying to figure out how to do programming for distributed systems in a better, easier to understand way. And right now, I want to kind of give you an overview of some of the things in Aura that we have in Aura, some of the motivations. We're going to start with a simple example of a distributed system that needs some access control. So here we have two users of the system. We're going to use the word principal to talk about users. So Alice and Bob are principals, and they're connected over network to each other and also to a jukebox, or a server which gives a jukebox-like functionality. And Alice and Bob are going to be able to request music from the jukebox using a signature, a remote procedure call that meets this signature. This is kind of programming languages notation for there's an operation called play for. It takes a song, and it takes a principal, and it's going to return an MP3 that represents that song. And note that here we've connected the return of the function to its arguments because the song S appears in both. So what might happen in such a system? Well, not a lot we can do, but Alice can request music from the jukebox. She conjures up a little request with the song Dancing Queen and her name. She sends it to the jukebox. The jukebox returns some data, again, representing the actual bits of that song. Now, this interface to access the jukebox is completely security oblivious. And what I mean by that is we just haven't talked at all about access control, who's allowed to play songs. And in fact, any principal who can connect to the network can make a bunch of requests and get a bunch of results out. And this probably isn't desirable, but it takes a little thinking to really put your finger on why. The reason this wouldn't be desirable is there's probably some sort of a policy put forth by, let's say, in this example, the copyright holders, the record company, explaining who's allowed to listen to music. And we can state such a policy really simply. So my statement of record company policy is that songs can have one or more owners. So essentially, if you've paid for a song, you get to be the song's owner. And once you own a song, you can share it with your friends. So you can authorize any principal, including yourself or including a friend, to play that song. So this is a really simple policy to write down, but it's going to be really interesting from the point of view of trying to build a system to enforce it. And there's three things that make this policy, this simple policy to state, hard to actually enforce. The first one is decision-making here is totally distributed. So in order for Bob to play a song, we have to figure out who owns the song. That's something that the music company is in charge of deciding. And then we have to figure out if that owner is going to let Bob play the song. And so we have two different principals who are acting together to make a decision. So that's hard problem one. Hard problem two is that there's mutual distrust between these principals. So if you think about, if you've read Slashdot any time over the last about 4 years, you know that people who consume music and people who hold the copyrights on music have very antagonistic relation. They don't like to talk to each other. They don't trust each other. And so it's not sufficient in this setting to just build one monolithic server and assume everybody's going to be happy abiding by its decisions about who can hear what. And third, there's a prominent use of delegation. And delegation shows up all the time in policies we want to reason about as humans, but it's actually really hard to get right in a computer system. If anyone here has tried to configure Apache or Subversion and really share your data in precisely the way you want to with your friends or your colleagues, you know it's hard to get right. There's a big design space, and it's pretty interesting. So what Aura does to address these problems is adopts a technique called proof-carrying access control. And what proof-carrying access control is is a notion that when we want to make an authorization decision, we're going to require that a process or principal presents kind of in hand a proof that they should be allowed to get access to whatever they want to access. These proofs, these access control proofs, are going to be composed of two different things. They have, first of all, standard rules of inference from higher order logic. So these are just rules that say, if A implies B and you can produce a proof of A, then you can use the combination of those like a proof of B. But also something new, which is what we call evidence. And evidence are cryptographic signatures which talk about what principles affirm or assert. So if Alice wants to play a song, she might write down her request and sign it, and that's going to be a piece of evidence that can show up later in proofs about access control. So in addition to building up these access control proofs, Aura has a runtime system which is going to be able to validate them. So it's going to read them in, use a type checking procedure to make sure the proofs have the correct structure. And when you say X follows from Y, it really does. And the Aura runtime is also going to log proofs in order to make sure, just as they come in and out of the system. And we'll see why this is useful and helpful later. I do want to point out that my colleagues and I, my co-authors and I, didn't come up with this idea of proof-carrying access control. And some of the ideas go back to George Nekula's work on proof-carrying code. And then also Lujo Bauer at CMU has used some of these ideas to great effect, actually replacing physical door locks in the CS building there with cell phone-enabled devices that send these proofs to open the door to your office. It's a very cool project, real inspiration. So how do we go back to our music playing example and enforce policy, the record company's policy about sharing and owning songs? Well, the general idea is we're going to take the original operation that didn't have any security constraints, this remote procedure call that talked about getting MP3s out, and we're going to add an extra argument. So now, in order to play a song, you've got to both talk about what song you want to play and who you are. You also need to provide, we can just read this, a proof that the record company says you may play that song. So in order to even make the remote procedure call, just to get the arguments to line up when you type the program, you need to actually be able to produce a proof of the right form that guarantees you can have access at runtime. And this is really, this is kind of the key property of programming in Aura when you're thinking about access control. So let's go back to our pictures and see how this would work. First of all, we're going to interpose some Aura code and a log between the jukebox and the other principles. And we're going to, just for our example, assume that at the beginning of time, everybody has a piece of evidence where the record company is asserting that it believes in the share rule. So this is, again, that rule that you can share music with your friends when you own it. And I'm just going to start out assuming everybody believes this. Now, if Alice buys a song from the record company, it's going to want to give her a capability or some evidence attesting to this. And so it uses a construct in Aura called say. It's going to run the code say owns Alice Take 5. And this is just the record company asserting that Alice is going to be the owner of the song. It's going to log that action and then get a digital proof about it. And the server can then send this proof to anyone it wants. The proofs don't have to be confidential. Now, Alice, on receiving her proof, could immediately turn this around, send it back to the record company, and get access to the song she wants. But she can also do something a little more interesting. And in this case, she's going to use a say construct in order to assert that actually Bob can play any of her songs. Again, this is going to reduce to a piece of cryptographic evidence. She can ship it out to Bob. And now Bob can take these three facts that he knows. He knows the record company believes in the share rule. He knows he's allowed to play Alice's songs. And he knows that Alice owns the song Take 5. So he can compose all three of those policy statements and get a proof that actually, according to the record company, Bob can play the song Take 5. So having done this, produce this capability, Bob can send it back to the server. We'll get another log annotation. And then Bob can get his music. So we've already seen that we can kind of use proofs to dictate who gets access to things. And now that because we've been logging carefully, we can also go back in later after the fact and send an auditor who can ask questions. For instance, the auditor might wonder, why was Bob allowed to play the song? That doesn't seem right to me. And he can look at the proofs that are in the log and see that the digital signatures, the evidence that came in when Bob was allowed to play the song, mentioned the record company because it asserted the share rule and that Alice owned the song. And it also talks about Alice's signature because she was delegating to Bob. And in the case that somebody wrote down a policy statement that was incorrect, we know that Bob was kind of blameless, and we need to go talk to the record company or talk to Alice about the way in which they're delegating their access rights. So audit gives us a way of kind of checking up on these policies after the fact. Now, that's kind of an overview of the beginning portion of my talk. And towards the end, I'm going to switch over. And instead of talking just about access control and audit, I want to tell you more about a confidentiality extension that I've been working on in Aura. And the reason we're interested in confidentiality is because access control doesn't give you all of the properties you might want in a secure system. And in particular, you can imagine that the server might send some MP3 over to Alice, and we have an attacker on the network who can just look at those bits in transit and get the song, even though the song's intended for Alice. Or perhaps Alice takes her song data and stores it to a disk, and it's shared storage. The attacker might be able to get it there. So what we're going to want to do is augment Aura so that it has a principled way of talking about confidentiality. We're going to do this using types to provide a specification for which data is confidential. And we're also going to be thinking about applying confidentiality, applying cryptography to individual data values and not to channels. And the reason for this is if you just open up a secure channel with some principle, you can communicate over it, but then you're often going to take that data and store it to disk, at which point it's no longer protected. So we take the view that if you secure your data, that's persistent and it's more valuable than just establishing a temporarily secure channel. And so the way this works in Aura in Aura, to give you a little notation, is that now we can change our play for remote procedure call so that not only do we get an MP3 back representing the song, but we're going to say that it's for the principal P, the one that requested it. And now, if our network attacker looks at the data, he's going to be confounded due to the underlying use of cryptography. So this is kind of a quick outline of everything I'm going to be talking about. Now I want to dive into just a little bit more detail about the story of access control and audit in this setting. So one important distinction that we're going to want to think about in this whole section is there's a distinction between the institutional policy that you want to enforce with a system. So you show up to work in your first day, you get a thick handbook from the IT department talking about what the computer use policy is. In addition, you want to make sure that you're not violating any social or legal expectations of resource use that are out there. There's a big human-level structure saying what you can and can't do with a computer system. And we can't actually enforce this institutional policy in a machine. What you can do in a machine is to take some formal rules that are written down in some machine-readable code and enforce those. And there's a tension and a gap between what you've instructed the machine to do and what you actually want to do, what socially and legally you're required to do. So Aura is going to help us narrow this gap. And it's going to do that in 3 ways. So first of all, we're going to include a really expressive policy language so that it's at least possible to write down the things that you want to write down. In contrast, you can think about your read-write-execute bits in your Unix home directory, where it's very, very difficult to write down the policy of who you want to share with. And typically, you can't do without going to an administrator to make groups or craziness. Aura is going to provide a better way to talk about policy. The Aura architecture is going to help us also create a small trusted computing base so that once we've written down a policy, we can have some assurance that the machine's actually going to be enforcing the right policy. And then lastly, we're going to use audit pervasively. And this principled pervasive use of audit lets us make sure that we have a method for finding out when things go wrong and refining policy. So let's look at how to talk about policy in just a little bit more depth in Aura, talk about formal rules. So as we saw in the example, we have a constructor in our policy logic called says. And here, when you write Alice says P, this is the proposition, which means Alice affirms that she believes P. And there's two kind of fundamental ways to prove that that holds. I'm going to use this notation actually use the pointer, of a colon to say this is a proof of that. So little p is a proof of big P. And if we put Alice's signature on a statement, then that's a proof that Alice says that statement, that Alice affirms it. So that's one way that we can get Alice to affirm something. The second way is we have an assumption the principles are, in some sense, reasonable. And if we have a proof that big P holds, we're going to assume that if we showed Alice that proof, she'd believe it, because proofs, you can't argue with a proof. Proof's true. So we use this notation return to Alice P, and this just means, this is going to say, let us conclude that Alice assumes big P holds. And this style of reasoning for access control has its roots in a language called DCC that Martina Body looked at kind of over the last 5 years. So what can we do with this? Well, one thing that's really cool is using a flexible language for policy, we can write a rule like this. So here we say, this says, Alice says that if P is a proposition and Bob says P, then P is true. What's going on here is Alice is saying that no matter what Bob says, she thinks it holds. So she's going to reaffirm anything Bob says, and we can think of that as her delegating all of her authority to Bob. Anything Bob does, anything Bob says, she'll say as well. And this is a really coarse-grained notion of delegation. It's, you're giving somebody the ability to do anything for you. This is a kind of delegation previous systems have been able to talk about in a really clean way. What Aura provides is a way of doing this in a more fine-grained manner. So now we have a more subtle rule where where Bob will act for Alice. Now Alice is going to say that if S is a jazz song and Bob says that he's allowed to play the song, then Alice will conclude that he's allowed to play the song. So now Alice is again delegating some of her authority, but she's not delegating all of it. She's only delegating it with regards to playing jazz songs. So this is following the principle of least privilege, and it's just being a lot more fine-grained. In order to get this sort of expressive power, Aura makes a decision that programs, when they run and need to put together one of these access control proofs, are going to be responsible for doing it themselves. The reason for this is that essentially the more expressive a language for writing down policies you have, the harder it is to search for proofs of those, to search for proofs that a policy access is allowed. And the examples on the previous slide actually aren't able to be encoded in a way that is really amenable for completely automated search. And so Aura programs use heuristics to do a good job of search in limited domains. And I think that's a very good trade-off. The underlying design principle is that we don't want to let the proof search mechanism constrain what you can actually write down. And so now I want to transition just a little bit and talk about kind of one of these institutional policies we might want to enforce and why we want kind of an expressive language. So this is a quote from a government website giving kind of a consumer-level view of what the HIPAA privacy guidelines are for accessing your medical records. The real details are, of course, much, much worse. But in summary, the government summary of this is that only you or your personal representative has the right to access your records, your medical records. A healthcare provider or health plan may send copies of your records to another provider or health plan as needed for treatment or payment or as authorized by you. And we can see kind of two principles in this rule. The first one is that at the end of that paragraph, it said a patient can direct who's allowed to access their chart. So a patient may allow access to their chart, and we can read this in principle in Aura as follows. If patient is the name of a principal, if A is a principal, and C is the patient's chart, then when the patient says that they can read the chart, that A can read the chart, then according to HIPAA, A can read the chart. And so this is just kind of a direct encoding of the delegation in the HIPAA rule. The second principle outlined in HIPAA was that medical providers can read charts. And simplifying this a bit, we're going to say that if we have a patient and D, who's a doctor, if D is the doctor of the patient, and we have that patient's chart, then HIPAA says the doctor can read the chart. So again, very reasonable. And you need a very expressive language like Aura to write this down. One thing that's interesting, though, is getting these rules completely right isn't quite good enough. And the reason is, in the real world, things can go wrong. And you have to ask yourself, what happens in an emergency? You have a patient in the hospital, they have a heart attack, they're unconscious, and they can't digitally sign something for you. It's not going to happen. If their doctor's golfing and we slavishly follow these rules, nobody can help the patient. You actually need some sort of escape hatches in policy sometimes. Aura lets you do that. Because we have audit, we can actually add escape hatches directly into our policy. And we can add this new rule that says, in an emergency, if we have a patient's chart and a reason that's just some text, HIPAA will allow anyone to read that chart. We know that anytime this rule is used, it'll be audited, or it will be recorded. And so as long as you have a system of audit, it's safe to add a rule like this, because you can always go back and look at exceptional cases and then judge by legal or social means whether that was a good thing. And so this is kind of a change in perspective from conventional access control systems. Usually access control systems are designed so that essentially if you don't know what to do, you immediately deny access. I would argue that there are a lot of real-world cases where the cost of false denies can actually be a lot higher than the cost of false allows. So the combination of this expressive policy language and a way to audit use of rules gives you a way to deal with these situations. Oh, go ahead.
So do you have to enumerate in advance all of the sort of escape clauses like this? Because it would seem that, what happens for an emergency, you can't figure out which policy you need to fall into. Is there like a sort of escape clause?
So in this particular case, yeah. So you can't write down just a truly generic escape all clause in a natural way. Actually, let me take that back. I hadn't thought about it, but I think you could. Using this rule, though, is pretty close. This is kind of the escape all clause for reading a chart. And you could either enumerate one of these for each security action you were concerned about. But I'm pretty sure that if you were clever, you could quantify over the action that you were going to take and allow a truly generic kind of escape all. Cool. And then Alan? Or? Okay, Ariel?
So who decide whether it's really an emergency? Does the system decide or the decides?
Right. So my take on this is that actually the system is never really going to be smart enough to decide what's an emergency. So what this rule says, the system has no idea whether there's an actual emergency going on in the real world. What you want is that, say, the nurses who work at this hospital and the doctors are going to know that they should only use this rule in the event of what, in their experience and training as a medical professional, they see as an emergency. And then later on, because we can audit every access that happens in the system, we can just run through the log and see, Tyler used the emergency rule on Thursday. Let's ask him about that. And then we can see if, presumably, he has a good reason for doing that, and it's okay. But if he didn't, then you'd have to investigate a little bit closer.
So this only makes sense if the people who can access the system are sort of a well-known group. So if they were just someone from, if I'm just a principal and not to access someone's records, I could say this is an emergency because claims an excuse, and then disappear only with every person. Just like in the hospital, everybody knows everybody, so they just trust them.
Right, exactly.
It's not to present credentials that say who you are. Right?
This is an alternative to rule-based, where it's as soon as you're in the system.
Yeah, and you could quantify things more closely if actually anybody who was a patient or a doctor anywhere in the United States was a principal in your system, you'd probably want another clause saying, oh, only hospital workers can use the emergency rule. Something like that. It just depends on where you draw the boundaries of the system. Cool.
You said that these systems
Right. Okay, so that's a really good question. So how does this fit in with heuristics? The place where the heuristics happen, let's step back. So I mentioned earlier on there's this gray system at CMU where they use cell phones to open their door locks. The way that system is architected is they've restricted the logic of access control so that anytime you pose a query, it's decidable whether or not that query is true. And so you can just throw it at a very robustly constructed theorem prover they have and always get an answer, yes or no, this should be allowed or not. In Aura, you'd have no chance of writing a general purpose theorem prover that could do this for the entire access control logic. Now, the kind of heuristics I was talking about for proof search are going to be specialized for the application. So for instance, if we might have a lot of rules that actually fully implement HIPAA and a heuristic that's maybe decidable over just the HIPAA rules, and then we can use that and always get a yes or no answer. Now, it may be the case that HIPAA is so complicated there's no decision procedure. I haven't investigated this. It would actually be pretty interesting. And if HIPAA is undecidable, then you can ask the system, let me see this patient's record, and the system says, I don't know. And at that point, you can ask the system very explicitly, let me see the patient via the emergency rule. Or if HIPAA is undecidable, you probably have another rule of HIPAA doesn't terminate, let me see the patient's record. You know, the heuristics are directed by the programmer, so depending on the application, you can essentially program whatever failure mode you want.
The system will be able to log the proof failure for
Yes. So if like the proof search for the HIPAA proof failed, you could log that. The way we have things set up, it wouldn't be logged automatically. The programmer would have to add code to show that that failed, but you could do it. Cool. All right. Oh, Tyler? Oh. All right.
Do you make a distinction between predicates that need to be logged and those that don't? So I can imagine emergency needs to be logged, but the other ones don't.
We don't currently, but that would be a useful thing to do. So in our prototype implementation, essentially every access to an external resource, whether it's through the network or whatever, gets logged. And this actually does a lot more logging than you'd probably want in practice. So one thing that we haven't really pushed on is just figuring out kind of how to optimize the set of things that you log, things that you don't log. And I've also been talking all along about kind of using digital signatures. And if you take that to mean doing an RSA digital signature computation at all of these steps during evaluation, you're going to run very, very slowly. But you can do a lot to do that lazily, to not generate signatures when you don't actually log them, things like that. But we haven't investigated it. All right, so let's move on from the policy language. So I was making this case that we have an expressive policy language so you can say a lot of things. And then there are two more prongs that I want to talk about of why Aura is a good platform for building your reference monitors. So the Aura system is going to let us build a small trusted computing base that is going to be, I claim, robust and useful for application development. So here I have a very rough schematic diagram. If you squint, you can see the Apache web server. And a conventional piece of software has a bunch of stuff. So in Apache, we've got the main application. It does some logging. It talks to the web and to the disk, to some resources. And it's configured by these .conf files that are all over the place. And if you want to figure out what's going on in the system, you need to be able to understand what compiler flags have been passed in at the time Apache was compiled. You need to know about the global configurations, the htaccess files associated with each resource. It's a mess. And then you have to trust that the logging is being done correctly by Apache. If Apache itself is exploited, you have no idea what's being written into this log. So we have a giant trusted computing base. It encompasses the whole system. And so in Aura, we can improve on this a little bit. So we can go back to our music playing example. I'm just going to zoom in on the server and its resource. And we can make some finer distinctions within the system. So we have our application code, and it's going to be protected by typed interfaces. So what I mean is that when we read proofs off of the network, we can check them to make sure that they're always good proofs about access control. And when we want to get at the underlying resource, we need to pass well-formed proofs, again, allowing access control, into the underlying system. And so what this means is if we're worried about unauthorized access, the parts of the system we actually have to trust are only on the right and the left-hand side of these boundaries. We can actually cut out the application code from the point of view of making sure unauthorized accesses aren't allowed. And furthermore, if you think about what you write when you sit down to write your application as an Aura programmer, you don't actually write the underlying system kernel. And I should note, when I say kernel here, I don't mean Linux, the Linux kernel. This is the application stack, so the Linux kernel plus the Aura runtime. But you don't write that. You don't write the underlying resource you're accessing. You don't write the logging software. All you write is the code, maybe some code that generates proofs or some initial proofs to populate your policy. So the things that are custom are all on the left side of this diagram. And if you take the intersection of the things that you trust and the things that you wrote kind of one-off, it's actually really small. It's just the proofs. It's a little hard to see. But the proofs are the only thing in the system that absolutely must be trustworthy and are written one-off per application. And whenever we use them, they wind up being stored in the log. So we really have very little that we have to trust in an absolute sense. Then lastly, I want to mention that having this audit gives us a good way to do system refinement and to think about understanding what's been going on in the system. So, Salil?
Can you elaborate on what you mean by trusting proofs? So there's the process of generating proof, and there's the verification of proofs. And typically, one thinks of only verification is what you need to trust, and if someone maliciously tries to present you with a false proof, you will catch it. So what do you mean by having to trust the proofs portion?
So I'm coming at this from a shallower angle than your question. I'm making the assumption, essentially, that the adversaries in the setting are Dole-of-Yao attackers, and we believe digital signatures work like perfect black boxes. And so the only question of trust, then, with a proof is whether the proof was written down, the formal rule was specified in a way that abides by institutional policy. So not, is this proof object sound against attack, just, is this proof object expressing the right thing at all? So we're more concerned with misconfiguration or essentially bugs than with attacks against the underlying technology.
What do you mean for verifying these logical proofs? That there should be some. So what the programmer doesn't need to write the production procedure for verifying proofs themselves, right?
Right. So that's all in this kind of kernel section in the underlying runtime system. So both the logical kind of the proofs are expressed as proof trees, and this walk over the proof tree to verify that everything kind of marries up in the right way is in there, as well as the call to the cryptographic library to ensure that the evidence is well formed. Right, and so when something goes wrong, are you happy? Is that okay? Good. So then going back to this idea of audit, when something goes wrong in Aura, the natural response should be you should go look at the logs, try to figure out what happened. The system design is going to guarantee, in a way I won't get into today, that essentially there's a one-to-one correspondence between interesting changes to the outside state of the world and log entries. So you can always know which log entry corresponds to which thing happened to your resource. And as we saw in the beginning, if a principal's signature doesn't appear in the log entry associated with some action, we have a pretty good way of exonerating them from blame in this situation, for having caused that state change. And now there's one problem with this view as it is, which is that if you're a malicious principal, you might put together a really convoluted proof to grant yourself access to some resource, which includes all sorts of irrelevant signatures, just to get other people's names in that log. And that's bad, right? We don't want this. And Aura provides a way of getting around that. The idea is that we're going to take some really convoluted proof, and we want to be able to come up with a simpler expression that doesn't unnecessarily implicate other principles for an action. So and you don't have to really understand this except that it looks complicated if you don't want to. So to be a little more concrete, if we have a signature from Alice and a signature from Bob, we can put those together into a big complicated proof that in the end only concludes that Alice says P. And it includes Bob's signature, even though it's kind of irrelevant, right? If we have Alice's signature, we shouldn't need to know anything about Bob to conclude that Alice says P. And what we'd like to be able to do is to take this complicated thing and come up with a clear proof where we just conclude Alice says P by the fact that there's a signature. Aura does this using a proof reduction technique that's kind of well studied in the programming languages community. The idea is that we do kind of two things. We use the Curry-Howard isomorphism, which is what programming languages people love to talk about all the time. We essentially translate our proof structure into lambda calculus terms, and then we can use normal lambda calculus evaluation to do simplification of terms. So we can take our encoding of our convoluted proof, which happens to look like this. We use a well-known simplification procedure, and we get the proof associated with the simple conclusion. And these are the only technical theorems, but they're pretty good ones, so I thought I'd put them up. If you recall your programming languages course way back when, lambda calculus is one of these things that's Turing complete, so if you try to evaluate it, you might get into trouble because it could loop and who knows what. But we actually showed for Aura, actually my thesis, I only showed it for a subset of Aura. Lehman Jia just wrote a paper where she extended this proof to the full system, showing that if we take two proofs, there's some non-determinism when you try to do reduction. The non-determinism is inessential. So if we have P, and it can either go to P1 or to P2, so we start with a term, we make a decision, go to there or to there, that you can always get back to the same place. So it doesn't matter what order you evaluate things in. And the second theorem says that if you evaluate long enough, you'll always terminate. So this gives us a deterministic total algorithm for proof simplification, which I claim is really useful for doing inspection of logs. You could yes, I think it's doubly exponential or tower of 2, like huge. So you can get bigger in the size of the term, but you should throw out all of these irrelevant pieces of proof evidence. Essentially, if a piece of proof evidence isn't being applied someplace interesting, it's being supplied to some function that's using it in a way that's discarding it. So we're getting simpler in that there should be fewer proofs. There should be fewer signed pieces of evidence in a proof at every stage of reduction. And so then you go all the way down. And
I'm just asking this really practical notion of improvement in the sense that abstracting common subgroups out goes away here, right?
Right. Right. So if you want to do it efficiently, probably, if the notion you care about is getting the fewest number of signatures in the proof, I think what you actually want to do, instead of normalizing all the way to the bottom, is to essentially do all the reductions where you're applying a function to a proof object and see if those disappear. And I think that leaves common subexpressions in a good state when they're essential. But yeah, I don't have a concrete answer on that. But I think you can do something smarter. The other thing you might ask is for clients to give you proofs only in normal form, and then you don't have to pay the cost of expanding them on the server side. All right, so in the last couple of minutes, I want to talk about the confidentiality extension for Aura. So this is new work. I just sent a paper off to ESOP about this. And if you recall, at the very beginning, we mentioned this case where you might send some data over the network. We know we're sending it to a place that it should go, but an attacker might be able to read those bits and snoop. And that's bad. The real world contains a lot of data where we don't want attackers to be reading our information, financial data, medical data, and so on. I'm not going to spend a lot of time belaboring this. And in AuraConf, so AuraConf is an extension that we wrote where we want to connect cryptography and confidentiality, encryption and confidentiality to the basic Aura language in order to provide some guarantees about confidential data. And following on the Aura idea that audit matters, we want to be able to audit decryption failures. And I'm going to claim to you that decryption failures are interesting to understand. So we'll get that in a sec. So first of all, let's see what can cause a decryption failure, and then later on I'll show you how we can learn from them. So we have Alice and Bob. They're actually both UPenn students, and they've been watching the World Series. They're going to go out tonight, and the Yankees are going to get their well-deserved drubbing. And in preparation, Alice wants Bob to join her for a cheesesteak and a beer ahead of time. So she's going to take a string representing this message, encrypt it, because she's also a security researcher, send it to Bob. Bob will decrypt that string, get her text, and he can make a decision. Everything went okay. Now, lots of things could go wrong, too. Alice could try to send her message. Some misconfigured routers or maybe an electrical strike on some wire could flip some bits, and now Bob's going to receive some junk and can no longer decrypt her message. Another reason Bob might get a message he can't decrypt, well, maybe some malicious user sent Alice a message, told her to forward it to Bob, and she did, and now he gets some junk and he can't decrypt it. Maybe Alice herself is malicious, and again, Bob's going to receive some message he can't decrypt. But if we're not doing anything careful, Bob's not going to have enough information to distinguish these possibilities. And they're really different, right? In one situation, something went wrong, we should probably retransmit. Down here, the user we thought is our friend is trying to send us bad data. These distinctions matter. And in order to explain how we're going to audit this, I want to tell you a little bit more about how AuraConf works. I have to apologize for this slide a little bit. I used some notation from Haskell, which kind of obscures the meanings of things. In Haskell, they use a data type or data abstraction called a monad a lot. And monads have an operation called run, which is used to make something, and return, which is used to make something, and an operation called run, which is used to consume it. So in order to make some ciphertext, we're going to use the notation run Alice42. So this is going to make a confidential computation for Alice, which we give the type int for Alice. The for tells us it's confidential for her. And when we evaluate this, it's going to reduce to some ciphertext. The way we can read the ciphertext is it's an encryption using Alice's key of the payload 42. And just so we can model things a little more precisely, we're going to throw a random number in there so that if we encrypt the same value for Alice twice, we don't get identical representations of that encryption. We want them to look different because we use randomized encryption in the real world. We'll also get some metadata. The other monad operation is called run. This is the one that consumes a value. And so if we take return to Alice 42, we run that, we evaluate that, and then we run the expression. We're just encrypting and decrypting. We get the value out. Now, it so happens that decryption is this interesting operation that can fail. And there's a bunch of reasons it might fail. Well, we might try to use the wrong decryption key. We might not have the right one available, so we can't decrypt. Maybe we can decrypt OK, but what we get out isn't a well-formed value we can analyze. Maybe it's some Aura code, but it's not well typed. And maybe we just get some ciphertext that's totally corrupt, and we can't do anything with it. In all of these situations, Aura is going to say that run of the expression evaluates to some e prime, where e prime blames a proof, p. And we'll see more about these proofs in a sec. So where do we go from here? Well, in AuraConf, we have kind of a language design around using these operations for encryption. And there's a tension that underlies everything. And the tension is this. We've got some expression, it has a secret in it. Is it good for people to be able to look at that expression? Well, if you're a type theorist, the answer is yes, it's great. You're going to want to take this expression that has secrets. You're going to want to throw some fancy analysis at it, maybe information flow. You're going to want to take this thing containing secrets and look at it as deeply as possible. If you're instead a cryptographer, what you say is, this thing has secrets. We should make sure that we do something to it so that it's computationally indistinguishable more or less from noise. We want you to not understand anything about the secret. And so there's this tension here between how programming languages people and how cryptographers might view secrets. And by the way, that's Alonzo Church and Bruce Schneier. So this tension gives us kind of three concrete technical challenges. The first one is going to be that the notion of what type a program has becomes relative. And what I mean by that is, let's think about Bob. Bob is going to send a message back to Alice. Here it's just the string toaster. And he can run that, he can encrypt it, and he gets some ciphertext. Now, because Bob was the one who did this encryption, he knows kind of where the ciphertext came from. It's a bunch of bits, and he can't do anything with the bits, but he knows their provenance, he knows their history, so he can deal with them in a reasonable way. If Alice gets this ciphertext, well, she has her key. This is what makes Alice Alice. So she can deal with this. She knows how to decrypt it, and she can look inside and figure out that, yeah, this thing is an int for Alice, using her private information. But if we take some other principal, some Charlie who's on the side, he looks at this, he has no idea, right? It's just a bunch of bits. And what's interesting about this is the notion of what type an expression has in Aura actually depends on what keys or what resources you have when you look at that. And that's reasonably new. The solution to this challenge in Aura Not is we're going to use this metadata that I alluded to earlier to guide how we type ciphertext. If we take a bare piece of ciphertext here, so this is just a ciphertext, we're going to say it has the type bits. But we can also stick metadata on. And so we write cast ciphertext to int for Alice, which is going to mean take the ciphertext, consider it to be an int for Alice. And we can do this in a couple of cases. If you're Bob in our previous example, you can do this because, like I said, you know the history of the text. You recognize those bits. So you can use this sort of reasoning. If you're Alice, again, you can use this sort of cast in order to, by decrypting the ciphertext and checking for yourself that it really is an int for Alice, and you're in good shape. Now, what about Charlie? What happens when you're in a system and you need to convince some other principal who doesn't have any special knowledge that something is an int for Alice? In that case, we're going to use what we call a justified cast. And a justified cast is just like a cast up here, except we're also going to say blaming P. And what that means is that we're going to attach a proof that will be associated with this bit of ciphertext. So in particular here, P is going to read that somebody says the ciphertext is an int for Alice. And now when you try to use something that looks like this, like it's an int for Alice, in particular you're Alice, and you try to decrypt this, if your decryption fails, you can look at this proof and say, wow, see, Charlie said that this was a good proof for me. Said that this was a good ciphertext for me. I can blame Charlie for the fact my message failed. So let's go back to our example of Alice and Bob before the Phillies game. So now if Alice sends Bob a message and the bits are just all askew because there's been some noise on the network, with overwhelming probability, it's not the case that the ciphertext got messed up and then the digital signature on the proof got messed up in a way that everything matched up. So we just get something ill-formed. Bob knows to ignore the message. And transport layer can take care of this. Not a big deal. In the case where our pirate Mal sends a message to Alice and attaches a proof saying, this is an int for Bob, pass it along, and she does that, Bob can decrypt the message, find out that there's a failure, but the proof is going to wind up blaming Mal because he needed to attach something to the message sent to Alice. And so Bob knows who's at fault. And in our last case, where Alice is actually the bad principal, again, her proof needed to appear, or a proof by her needed to appear on the message in order to send it over. So Bob knows, again, who to blame. So that's challenge one, this idea that it's hard to determine what types things have. You have to be careful when you're communicating about cryptographic objects, about ciphertext. The second challenge is that, as I alluded to, we have this use of keys and principles that gets reflected into checking the types of things. And that makes the analysis of Aura programs really interesting. This is very brief. When you want to use types, when you want to use keys at runtime to do things like decryption or signing, we use what's called a type and effect analysis. So this is a really beautiful classic static analysis that goes back to the 80s, and that tracks what gets used at runtime. When we want to know about the types of things that have ciphertext in them, we're going to adopt some ideas from modal type theory, in particular from Tom Murphy's thesis. These are both kind of really cool theories on their own, and they join together in a nice way to let us understand Aura programs. The third problem is that there's a path dependence in your type checker. So let's go back to, we've got Bob, who's going to send a message to Alice, and he runs the code, return to Alice 3. What he gets back is a cast, a true cast, so just cast encryption into Alice. And if you're totally naive, Bob can't type check this. So we have kind of a novel evaluation semantics that can record the history of the computation, bits of the history of the computation, in order to guide the type checker in the future. So it's a lot of work to do that. And the question is, what do you get? Well, you get two things. First of all, you get this ability to audit decryption failures. And secondly, we get a non-interference property. And what non-interference means is we are going to run a thought experiment. So we take some secret that's a string for Alice. We put it through an Aura program that has Bob's key. So this program can't analyze that in any deep way. We'll get an answer. We'll get 15. Now, if we change the secret for Alice that we send through this program, we're going to get the same answer modulo some natural equivalences. And this is a really nice security property. It's unsurprising when you think about things from a cryptographic point of view, but it's really good to know that the language guarantees this. For one thing, that means you can optimize away some of the encryption, and the language is still going to do the right thing, as long as you're in a closed environment. So running short on time, I want to conclude now. So Aura, I think it's kind of an exciting system. It's a single language that unifies kind of functional programming. We didn't see a lot of that, but also access control confidentiality. Has a very rich notion of access control language, and the feature set is, in my claim, really compelling, and leave it at that. So lastly, just want to thank all of my co-authors on this work. They did, couldn't have done nearly a fraction of this without them, especially Steve Zadanswick, my thesis advisor. Great guy. So, yeah, any questions?
So this may be a very naive question. Going back to examples for access control, I really understand how they very useful. Can you give sort of real-world example for encryption failure auditing and why that would be very helpful?
So I think that the real value in it is that if you're in a system where you're running over confidential data, and you start getting a lot of decryption failures, it gives you a way of distinguishing between whether you're under attack versus whether there's just some noise on the network or things like this. So I'd claim it gives you a way of understanding malicious activity from kind of random bugs. That's a very good point. Cool. Tyler?
Do you have any sense for how kind of auditing that your system would require compares to the kind of auditing that is currently done today? Like, there is auditing that's done with clients. Would you have any hope of maybe translating that into this sort of auditing?
I think so. So I haven't done this work but there are people who are looking at taking real systems like medical systems or looking at like HIPAA policies and building formal models and looking at audit through that lens. And I think you could do the same sort of thing here, though I may not be answering your question. Ron?
Addressing confidentiality, I wonder about the secrecy of the proofs themselves. Alice sends a proof to Vaughan, can she have a proposition themselves be encrypted so that Carol cannot see, for example, which is the friend of Alice that authorized her to play the song?
Yes. So, well, let me answer that first. So everything composes in a really nice way. So Alice can send a confidential message to Bob with a proof attached to that, and then she can just encrypt that again under another one of these 4 types and get. So if Alice is sending a message to Bob with a proof, you can encrypt proofs just like any other type of data.
So you get that for free from both being first class.
That's right.
And the same question, what about Alice trying to convince Bob that it's zero knowledge without actually revealing even to Bob which is the friend of Alice?
I think that's really interesting. I've thought about it a tiny bit, enough to know that it's pretty hard. I think what that comes down to is you need an efficient zero-knowledge proof system for essentially looking at first-order, demonstrating the validity of a first-order statement in a statement in first-order logic, or equivalently demonstrating that a term in type theory is well-typed. And I don't know, I'd be very interested to look at that in detail. In about 10 minutes, it was not obvious to me how to do it. Salil?
Do you know anything, have you looked at all to the cryptographic soundness? So I know some people have looked at kind of showing cryptographic soundness for Dole-Yao models.
I haven't. So it's actually really interesting. Michael Bacchus has this framework that in Isabelle Hall, where he shows, using Isabelle Hall as a theorem prover, to show that he has a particular Dole-Yao attack model is cryptographically robust. And we have, very frustratingly, a giant cock proof that, that the system works. And those 2 different formal methods, tools, don't talk to each other. So if somebody were to take the work and redo Michael Bacchus's work in cock, or if I were to take the work and re-demonstrate the soundness of Aura in Hall, you'd hopefully be able to compose these in a nice way. There's a little bit of a mismatch beyond just the different systems. In particular, we use kind of a very algebraic formulation of the cryptographic objects. Michael Bacchus's is based on assuming essentially a trusted third party, and then you compile that third party away. But I think you could make that work. Steve?
Is the blaming for decryption failures, is that the dual of the CRCS operator, or is there also some notion of the failure of verification of signing?
That's a good question. Initially, I'd hoped that encryption would be a much closer formal dual to signing, and there are some technical reasons why it doesn't quite work out. But yeah, so I don't actually know. But there's definitely some connection. Just confidentiality seemingly always winds up being dual to integrity. So you'd expect that. Cool. Thanks.